Yes. Good afternoon. I'd say this will be good evening. So three of you are there. Let us wait 2 more minutes.
Sir, I have a unrelated doubt, sir.
Yeah. Then,
Sir, in P block, right, sir? Like
hmm,
uh, both 11th and 12th.
hmm.
How important are the preparation for some compounds? Like, for example,
Not required. You really don't have to concentrate on the reactions part. None of the like I'm talking about JE, right?
yes, sir.
So for that, reactions are not that important. You don't have to really worry about the reactions, but the properties, say for example, the oxyacids, the structures of all the compounds, the allotropes properties, like say how melting point varies, how atomic radius varies, what are the exceptions. That way,
Hmm.
it is important. Not the reactions part. You don't have to worry about the preparations. Nothing. You don't have to worry about the reaction part at all. The questions also will be if they're going to ask questions from those sharp like those areas periodic table, they'll generally be asking about the trends, like how periodic properties varies along the open periods, and obviously the structures. That if you know chemical bonding, like if you can easily answer those questions.
Yes, sir. Sir, I saw this question, sir. Uh,
Hmm.
that said H3BO3 and then
Hmm.
hyphen,
Hmm.
arrow,
Hmm.
delta A, and then again gives delta with heat gives B, with heat gives C, sir. Identify C. அந்த மாதிரி
Oh,
கேக்குறாங்க.
okay. Okay.
The
That's
answer
what
was
H3
H3B4O7
PO2.
something.
Oh, H4B2O7. அதான் சில இந்த நான் சொல்றேன் இந்த there will be like borax. This is what is called as borax.
Yes, sir. Borax only.
H4B2O7.
Yeah, yes, sir.
So அதான் like this, if at all they ask, it will be very rare. And if they ask questions like this, generally it will be from trends. But yes, important. There will if you just look see the previous year papers, you will be able to understand from which areas they're asking the reactions from, and they'll actually be repeating. They will not ask out of nowhere some new reaction, which is like some corner of the book. That way, they will not be asking. Say this borax preparation is actually a very important stuff, right? But again, uh, probability of questions coming would be less.
Yes, sir. Okay.
Okay. So I would strongly suggest you don't have to really go through the entire this thing. So you just collect say from past 30 years questions from D block and all these entire periodic table, right? So if you just collect and if you just go through that and get the answer, then that would be enough. And eventually we'll be doing questions. I have planned like a quiz kind of stuff. Just read and come, and then we'll be doing a quiz. So anyways, when if that time comes, I'll tell you how exactly it's going to work. It'll be the last part because I hate inorganic, right? Except for coordination compounds. Okay,
Okay, sir.
so right, so we have only still more 4 people. Okay, we'll start. Right. So we were saying gaseous states. If you all can remember yesterday, right? We were almost the verge of completing the chapter, right? So there's just one small part left, and we'll go for problem solving. Okay, fine. So we are going to study about liquefaction. Right. Fine. So tell me, guys, you must have really at least heard this term, like liquefaction. The first question is, what is liquefaction? Or if I have to ask a better question, assuming that you know a little about liquefaction, what is the difference between liquefaction and condensation? So I think it's a form of a clue, right? Hope you understand that in both condensation as well as liquefaction, I will be converting gas to a liquid, right? So if that's the case, what is the difference? That's a similarity. Difference between condensation and liquefaction.
So liquefaction is by compression of
Hmm.
things,
Hmm.
but then
Okay.
condensation requires some melting points and all that.
Okay, so like say almost correct. So like condensation is gonna be both. I'm gonna convert gas to a liquid. There are two ways of doing it. One by definitely cooling by reducing the temperature of the gas, and that is what is condensation, right? So here in liquefaction, yes, I'm going to apply pressure. I'm going to compress the gas, and thereby I can convert it to liquid, right? So that's the basic difference, right? Liquefaction, I use pressure as the criteria, and there in condensation, temperature is the criteria. Right. Okay. So like it's very simple. I just have a gas, right? So there is a piston and I'm going to apply pressure and these gas molecules are going to come closer and closer, right? And they will eventually form liquid, right? Okay. So now if I see the form of a graph, right? So that will actually give me a lot of interesting facts about liquefaction. You just see it's a simple process, but it's not exactly, right? So if I plot a PV graph, right? So I assume that the pressure was very less, right? Uh, Correct? Okay. So the pressure was very less and the volume was very high. Right? That's what you see. Lower pressure. This is lower pressure, higher volume. This is how the gas. This is where the gaseous state exists. Right. Now what you have to do is you're going to increase the pressure. Right. You are going to decrease the volume. Right. That's how the graph should go. Right. So if you look at the liquefaction curve, it is going to be something like this. It's going to keep on like this. Okay. Now at a point of time, at a particular pressure, right? At a particular pressure, and when the molecules are really close enough, right, the liquefaction starts. Okay, that means the gas molecules start converting themselves into their liquid states, right? Okay, now at that time what happens is the volume the what is it the what is it the pressure is not going to change, right? So you will see something like this. Am I doing it correctly? Liquefaction curve. The pressure cannot be. Okay. Something like this. Not exactly like this. Say something like this. Okay. So what you see here is after this particular point, right? The change in volume, I would say the change in pressure is not going to be that much, right? And like this is going to happen until all the gas molecules are converted into the liquid state, right? Now, once the gas molecules have gone to the liquid state, right? Now you will see, irrespective of how much ever pressure you supply, right? Irrespective of how much ever pressure you supply, the volume change is going to be negligible, is it not? Because liquids are almost incompressible, right? So like after this is the point where the liquid state starts, right? I mean, all the gas molecules have converted into the liquid states. This is the point where the liquefaction started, right? The gas now, till from this point until this point, you will see that there is going to be an equilibrium existing between the gaseous molecules and the liquid states, right? Okay, and obviously the equilibrium is going to move forward and forward and forward, and eventually you will see all the gas molecules converting into the gaseous state, right? So after that, if you still more increase the pressure, right? If you still more increase the pressure, so what will you see is the pressure you can keep on increasing, but you will see the liquid will not be compressed that much. The volume change is going to be negligible, right? So almost like a curve like this, right? This is what you will get, right? Almost a curve like this. You'll see almost the volume is constant even though the pressure is varying, right? So this is how the curve looks for any liquefaction. And obviously this is going to happen at a particular temperature, say T1, right? right? This is going to happen at a particular temperature T1, right? Now, if I increase the temperature, right? If I increase the temperature, now tell me guys, whether it's going to be tougher to liquefy the gas, or it's going to be easier to liquefy the gas if I increase the temperature?
It will be difficult.
Difficult, obviously, right? So you see, if I have, say I'm going to have hydrogen gas, right? Hydrogen gas, H2, right? Say this is at 50 degrees Celsius, right? Another case, say if I have an same H2 gas at same initial pressure, assume that it's all open to the atmosphere, all are 1 atmospheric pressures, right? Initial pressure, right? Say this is at 100 degrees Celsius, right? Right now, what you have to understand is, obviously here it's going to be difficult. Difficult in the sense you have to supply more pressure, rather than say if you supply 5 atmospheric pressure. I'm just giving you a random number. Say if you're going to apply say 5 atmospheric pressure for here, for the gas to get liquefied, maybe here you have to give 10 atmospheric pressures, right? But again, the values I'm getting are very less. It will be around 600, 700 atmospheric pressures generally, right? Okay, so anyways, you understand, right? If I have higher temperature, it is going to become difficult for the gas to get liquefied, right? Okay, so now say at temperature T2, if I'm going to plot the curve, right, say same initial pressure and same initial volume, if you start the graph with, right, so you will see that the graph is going to go something like this again, right? So if you compare, obviously I see like the pressure starting point where the liquefaction starts for the previous T1 and where the liquefaction starts for this one, obviously it happens at a higher pressure, right? Hope you understand. Obviously the volume is going to be same, right? So you'll see that the liquefaction is going to start at a higher pressure. Now again, one more thing what you can observe from the graph is that the equilibrium, that is the distance, the time at which the equilibrium is going to exist. I said that the equilibrium is going from the liquefaction starting point to the point where the entire gas has converted to liquid. There's a particular time frame, the equilibrium time frame. That time is going to decrease, right? So at a higher temperature, right? So now say if you're going to still more increase the temperature, and if I plot another curve, something like this, right? So if you keep on doing it, if you just keep on increasing the temperature, and if you look at it, I am going to have something like this. Okay, now this is what is called as the point of inflection. Okay, anyways, the terminologies are not important. So what is important is how is it that you're able to visualize this, right? So at a particular temperature, say some Tn, right, you will see there is no liquefaction starting point, there is no liquefaction ending point, meaning that the gas cannot be liquefied, right, after a particular temperature, irrespective of how much ever pressure you supply, right? Even if you supply, ideally speaking, infinite amount of pressure, right, at the beyond the particular point, beyond the particular temperature, you will not be able to liquefy the gas, right? So that particular temperature above which, irrespective of how much ever pressure supplied, the gas cannot be liquefied, that temperature is what is called as critical temperature, right? It's always what is called as critical temperature, right? So that's the exact definition I gave you. Above this, or like in a different way, if I have to specify it or define it, it is the minimum temperature, or I would say this is the maximum, sorry, not minimum temperature, it is the maximum temperature at which the gas can be liquefied. Beyond that, no. If you're just going to increase the temperature, you cannot liquefy the gas, right? Now, and I'll answer this question from whatever you have understood now. If I want to easily liquefy the gas, right, I should have higher critical temperature or lesser critical temperature.
Lesser.
Okay, lesser. Okay, so we'll just give an analogy to. Just give try to understand the situation, right? Say say I have a gas which is having a critical temperature of say 10 degrees Celsius, right? I have a gas which is having a critical temperature of 10 degrees Celsius, right? Say I have another gas which is having the critical temperature of say 50 degrees Celsius. Okay, now tell me which gas can be liquefied at room temperature itself.
The 50 degrees Celsius one.
Obviously, correct, because this is the maximum temperature at which the gas can be liquefied. That means this is below room temperature, right? So that means this gas absolutely cannot be liquefied at room temperature, right? But this, I can even start with 25, right? Till 50, it's okay for me. Till 50, if I go, right, still the gas can be liquefied. Correct. So obviously, a gas having higher critical temperature is actually more feasible in terms of liquefaction. Okay, remember this point, right? So the gas with higher critical temperature will be can be liquefied with more ease than with than gas with lesser critical temperature. Okay, right, fine. So obviously, you at the particular critical temperature, you are going to have a particular pressure and particular volume. Correct. So that particular pressure and that particular volume are what are called as critical pressures and critical volume. And how do you represent it? TC, PC, and VC. Right? Temperature, pressure, and volume at critical points. Right. Okay. So obviously, this is what is the the observable quantity. These two are mathematically derived. Right. So there are formulas for critical temperatures, and this is like okay. Now one more point I want to tell you is now you see guys, if the gas was ideal, right? If the particular gas which you're talking about is ideal, what can you comment about its liquefaction? Obviously here with what you are seeing is a real gas case, right? So if the gas was ideal, what can you comment about its liquefaction process? Anything, whatever comes to your mind.
So can you repeat the question?
So what I'm asking is, what you're seeing here, whatever is happening is for real gas, right? So if the gas is ideal, what can you say about the process? Anything, whatever which comes to your process regarding an ideal gas liquefaction, what can you say about it?
Sir, it won't liquefy that easily.
Okay, correct. Right. So the thing is, ideal gas is a gas which cannot be liquefied, ideally speaking. Right. Now you see from the graph itself, you can understand only at the critical temperature curve, I see that it's exactly matching the ideal gas equation curve, P versus V graph. Right. But in all the other cases, till some point, right, till the liquefaction starts, it's okay. But when the liquefaction is starting, the curve is actually varying. Right now, this is one way of looking at it. The other way of looking at it is from the kinetic theory of gases. We said that gas molecules are not going to have any force of attraction between them. And again, if that's the case, it's impossible again for us to liquefy the gas, because in liquid state, I'm going to have higher, or say obviously some force of attraction is going to be there, right? So two ways of looking at it, right? So ideal gas cannot be liquefied. Okay, fine. One more question I want to ask, not with respect to liquefaction, but this is just a point which I forgot. Right now, tell me, what should be the conditions of pressure and temperature so that the real gas can behave ideally? Again, I repeat the question. What are the conditions of temperature and pressures so that a real gas can behave ideally?
Boil temperature and boil pressure.
Okay, that is the technical way of saying it. But I'm asking, say if it's going to be high, it is going to be at a higher temperature or lower temperature, or it's going to be at higher pressure or lower pressure. That way I'm asking.
Sir,
Room
lower
temperature is
pressure, higher. Okay.
One by one. Anybody? Yes, now both of you are silent now.
Sir,
Ah,
low temperature and high pressure.
low temperature and high pressure. Okay, fine. Was it the same, Stevenson, what you're going to say?
No, sir.
I hope. Ah,
I sir, does it have volume? Does it have something to do with volume?
yes, it has something to do with the volume.
Okay, then
Correct.
high volume, low pressure, sir.
And tell me in terms of pressure and temperature.
Oh, pressure and temp. Okay. Okay, low pressure, high temperature, sir.
Low pressure, high temperature. I think low pressure, high temperature. Okay, fine. We'll check. Right. Fine. Anyways, I don't like exactly remember, but still, it just takes a few seconds for me to think about it and give an answer. Okay. So basically, what are you trying to do here is you are trying to make sure that the postulates or the points given in the kinetic theory of gases becoming valid. Right. So one thing is that one thing is about the interactions. Right, interaction regarding interaction, kinetic theory says that there's not going to be any interaction, right? Okay, next next thing is about the volume, right? So volume, what it says is compared to the individual gas molecules, right? And I compare it to the what is that, the whole vessel's volume or the entire gas's volume, the individual gas molecules' volume is pretty negligible, right? So what you can understand is, if I don't want any interaction between the gas molecules, right, obviously they should be as far away from each other as possible, right? That makes sense, obviously, right? They should be as far away from each other as possible, right? Only then obviously I can say that this and this cannot influence any force on each other. They should be very far away from each other. Okay, that is one point. Next thing is, if I want to neglect the individual gas molecules volume with respect to the whole volume of the gas, right, obviously the volume of the vessel, or say the overall volume of the gas, should be pretty high, very high volume, right? I hope again you can understand what I'm saying, right? I should have very high volume of the vessel, or say very high volume of the overall gas, so that I will be able to neglect this particular small volume, right? So what do you understand is, now this way I'm telling about I should have large space between the atoms so that they cannot exert any force on each other. And second way of looking at it, if you want to neglect the volume of individual gas particles, obviously the volume of the overall gas should be pretty high. So either way, I'm saying that the volume of the entire gas or the volume of the vessel should be pretty high. And now this, if you understand, now going for pressure and temperature is very easy, right? So I should have very high volume, right? So obviously I should have very less pressure if you want to have very high volume. And obviously, if you now in terms of temperature, if you see, for attaining very high volumes, I should have very high temperature. Okay, now why I stressed upon this point is because this came as a question in JEE Mains, that what they just gave options. Real gas can behave ideally A, B, C, D, high pressure, low temperature, something, right? So you have to make sure that you are going to have low pressure and high temperature, because I want the volume to be pretty high. Okay, right? So hope this makes sense, right? So yes, that's about this chapter. Okay,
Sir, from the equation, right, sir, that says P plus A n square by V square
Yeah,
into V minus
yeah,
NB.
yeah.
So now, so I try to convert that into PV is equal to nRT. So for
Okay.
that, since there was a plus, I thought it should be less. So instead of
Okay,
V
okay,
minus,
yeah,
V
makes
should be
sense. Oh,
minus.
I understood what you're telling. Yes, makes sense. Yes, right. Okay, so fine.
Sir,
So
so
next thing is,
such
yeah,
analogies will work, sir. That's what I'm asking.
yes, it would work, but you should be little good at mathematics for that. If you're good at mathematics, yes, it will work, right? Because all these things we derive from the theoretical concepts. So if theoretical concepts are going to work, yes, mathematics should work, ideally speaking. But again, I would suggest be very choosy, like in the sense that sometimes it is not a good. You will get the answer for sure, but sometimes getting mathematically the answer might become little tedious. It become a long process. Rather than if you just apply, if you just think about it, think about the concept, practically apply it, then actually it's a say shorter way, or say it is a less time consuming way of getting the answer for these kind of questions.
Yes, sir.
right? Okay, fine. So what I was telling, yeah. So there are a few more points left about the liquefaction, right? Okay. Now next thing is again mathematically we can derive this for easy liquefaction, right? So for easy liquefaction, right? So in terms of the van der Waals constants A and B, right? I can speak about it. Again, this can be mathematically derived, right? So it is, you should have a very small A, right? And a large B, right? Like for example, they'll just give you two, three gases having some A and B values and ask you or arrange them in the order of ease of liquefaction, right? So you must understand that I should have a small a and a large b. Now, again, this will make sense if you can understand what is the role A and B are playing in the van der Waals equation. Hope you remember A is for volume correction, right? A is for volume correction and B is for force correction. Hope you remember like this. If you can know this, right? If you know this, then understanding why I should have a small a and a larger b makes sense, right? So obviously now if you want to convert a gas molecule into a liquid phase, obviously same temperature and pressure if I take, the volume of gaseous molecules are going to be very, very high, right? But what I need is that I want to reduce this volume to a smaller volume so that they become a liquid. Correct. So obviously that's why I should have a smaller A in the sense that in some sense that I should have a smaller volume so that I'll be able to easily liquefy the gas, right? And obviously I should have, if you want to liquefy a gas, and if the interactions between the attractive forces between the gas are pretty high, then it's again easy for us to liquefy the gas. And again, that makes sense about why I'm having a larger B, because I need to have higher force of attraction
Sir,
between the gaseous molecules. Yes.
so A is for force correction, right?
Uh, is it? What did I say? B is for, oh, correct, right? Correct, correct. A is for force correction. Correct. Is it smaller A? Ah, correct. Thanks for pointing it out. Let me check. Just give me a moment. Oh, yes, actually, it's exactly opposite. Thanks for pointing it out. Concepts are pretty same. Oops. Right? So I should have a larger because right, this is for force, right? And this is for volume. May I unmute? No. Okay, fine. So this is for force. A is for force correction and B is for volume correction. So obviously I should have higher force, so larger value of A, right? And I should have lesser volume, so smaller value of B. Okay, right? So yeah, thank you for pointing it out. Yeah, that's the condition for easy liquefaction. Okay, and I just have to give you the formulas for TC, PC, and VC. Once again, it's I don't remember these formulas as such. searching. Just give me a moment. Forgot. Right. So VC is equal to 3B. PC is equal to A by 27B squared, and PC is 8A by 27 RB. So these are the formulas. Okay. It questions might come, might not come, but again, they will not give you A and B values and ask you to calculate, right? So they might just one question came in the match the following kind of questions. They just give TC, PC, and PC on one side, and the other formulas and other they need to match it properly. And one more formula is there for boil temperature. That also I'll give you. I just saw it somewhere. Yeah, got it. So TB that is the boil temperature, the temperature at which the gas behaves ideally, is A by RB. Okay, this formula. Right. Yeah. So these are the things regarding liquefaction. Done. Right. So now we'll go for problem solving. If you don't have any doubts as such. Right. So let me bring
So
some
for
problems.
TC, it's
Yeah.
8A.
Sorry? Yeah, it's 8A.
Oh.
TC is 8A. Yeah. Right. Okay, let me bring some problems. Okay. Questions on your way. Check your group. Yeah, it's there. So you have 3 questions. Question number 8, 9, 10. Right. Okay, we'll just consider question number 8, right? So they say there is a 10 centimeter column of air trapped by a column of Hg, which is 4 centimeter long, in a capillary tube in the form of a uniform bore when the tube is held horizontally at 1 atm. Right now they're asking what is the length of the air column when the tube is held vertically when the open end is up, right? Okay, so spend some time on the question. So if you just look at the diagram, you'll be able to understand what they're trying to say. Say they have something like this. Okay, I mean, not exactly the diagram. It should be very thin. This part should be very thin because it's a capillary. Hope you know a capillary is going to have a very small volume, right? Okay, so this point is mercury. I would say, okay, a little bit if you can extend, right? So this point is mercury, right? And this point is air. This is mercury, right? Now this is in the this is in the horizontal position, right? Now if it's kept in the horizontal position, you can see this is 4 centimeter, and this is it's actually a physics problem. Maybe we shouldn't be solving it, but still we'll solve it. Okay, so this is 10 centimeter, right? Okay, now what they're asking, they say that is held horizontally at 1 atmospheric pressure. Okay, this gas is at 1 atmospheric pressure. Okay, right? Fine. The length of the column when the tube is held vertically, in the sense that if they have it like this, okay, bear with my diagram, guys, please. Okay, so if it's like this, then what is going to be the length of the mercury column? Length of the air column. Okay, whatever it is. If you can if I can find this one, obviously I can find this one. What are these both heights? Okay, I'll give you maybe 2 minutes. Just think about how we're going to solve it. Maybe we didn't see the formulas as such, but it's a very basic formula which you should be knowing. Actually, fine. Okay, we'll solve it. Okay, an idea of how to solve this? Okay, fine. Let me help you in this, right? Because it's in a little bit of not exactly physics, but still, right? Okay, fine. Now, first thing you have to know is how can you convert ATM in terms of mm of Hg, right? Hope you remember it's 1 ATM is 760 mm of Hg. Okay, or I can even write it as 76 centimeter of Hg. Either of it will work. Okay, so this is one thing, and one more thing is torr. Now remember, 1 torr is 1 mm of Hg, or I would like basically mm of Hg. That means 760 torr is 1 atm again. Okay, so these are some different units of pressures. Okay, volume I already told you, decimeter cube, meter cube, centimeter cube, ml, liters, right? Okay, fine. So this is one thing which you have to know. Right. So going to the question now, you see, guys, if this is held vertical, this is if this is held horizontally, right? Now there is no way that there is going to be any pressure coming from this side because it is not open to atmosphere, right? Okay. Now the only thing which you have is the pressure due to this. That's it. This is not going to exert any pressure, is it not? Only if it's vertical, this might exert some pressure on this. Correct. But in this case, this mercury has no role to play in deciding what is the length of the air column. Correct. Right. So this 1 atm corresponds to, you can just convert it in terms of mm of Hg. So if it's 1 atm, that corresponds to 760 mm of Hg. That is the only initial pressure. I would say this was the initial pressure Pi. Right. Okay. Fine. Now going here to this condition. Right, so you have this already, right? Now already this pressure was actually what, 760 mm of Hg, correct? By the initial pressure, and also I mean, sorry, already I had 760 mm of Hg. This is 1 atm. This is also open atmosphere 1 atm, but extra pressure you're going to get. Where is the extra pressure? This one, this guy, that is the some column of mercury is also going to exert some pressure. Okay, so initial pressure is only this 760 mm of Hg, or I say 1 atm. Don't confuse with the length of mercury and the 760 mm of Hg. Don't confuse yourself. It is just that 1 atm I have just converted in terms of 760 mm of Hg. So P initial is 760 mm of Hg. Right, now P final, if I take it, it will be 760 mm of Hg. Right, and obviously you see there is 4 centimeter of Hg also. 4 centimeter is basically 40 mm, right? So the final pressure is going to be 800 mm of Hg. Okay, hope you understand what I'm trying to do. Initially, the pressure was only due to the initial pressure given, that is 1 atm, right? But if I tilt it, make it vertical, you will see that this mercury column is also going to exert some pressure on this air column. Right, and I know what is the length of that. That is going to be 4 centimeter, or I would say it is going to be 40 millimeter. Right, so the final pressure is this much. Now that's it, problem solved. Now I can go for my Boyle's law. Okay, now you can understand. So where the hell is the Boyle's law coming from? How can I find volume? And don't worry, it is going to be like this. So I have, say, I know P1 V1 equal to P2 V2. Right, so P1 was only 760. Now volume, how will I write it? Is I'll write it like area into the length of the column. Right, now we're talking about only air, right? So this is basically the length of the air column. Initially, how much ever it was. What is wrong? Okay, right, now that should be equal to the final pressure P2, which is 800. Just now I calculated how is it, into the area, that is area into length is what is volume, right? So area into the length of the air column in the second case when the pressure is this much, L2, right? Okay, so A and A gets cancelled, right? So I know what is this initial length, so it will be 760. Now you see what was the initial length. Initial length was 10 centimeter, right? That was the length of the air column, right? Okay, so 10 centimeter, right, which is equal to the final pressure I know, which is 800. Okay, into the length which I have to find now. That's it, and that is what is the answer. They are asking you what is the length of the air column when I tilt it, right? That's what I can easily find out, and you will find the answer to be 9.5 centimeter. Obviously, you expect the pressure, the length of the air column to decrease, Obviously, right? Because there's extra pressure coming. So obviously you see initially it was 10. Now it would have become 9.5 centimeter. Okay. Everybody understood? So the only reason which I took this is because it involves Boyle's law, or else I wouldn't have taken this problem. Anyways, right? I hope everybody understood. Is there any doubt? If there's any doubt, you can ask me. Okay.
No
I
doubt.
hope. Okay, cool. So hope everybody understood. Now we'll go for the next question. That is an easier question. 9th question. I think I'm not going to solve it. You will only tell me the answer. Pretty easy. But again, you have to be good with percentages. Okay, the volume of an ideal gas is to be decreased by 10%, right? And that is done by increasing the pressure by X% under isothermal conditions. They're asking you, what is this X?
Sir, I'm getting it as 100 by 9.
100 by 9. Okay, check. Okay, anybody else? Is any other answers? One answer was 100 by 9. Anybody got the same answer, a different answer? Okay, again, it's just purely formula substitution of Boyle's law. P1 V1 equal to P2 P2. That's it. Right now, say I don't know what was the initial pressure, but they have given me in terms of percentages. So if I keep it as P, and if this say P1 is for some P and V1 was some V, they're telling the final volume and pressures are like this. That is, there is X% increase in volume. So I can say it is P plus X by 100 into P. Right? Okay. Because this is the increase in volume. This is the final pressure. Already some pressure was there. That pressure is increased by X%. Right? X by 100 into P. Okay. Now, oh, wait. Am I doing? Yes, correct. So now volume, they are telling is volume, the initial volume V plus 10% is increasing. So 10 by 100 is 0.1. So it is going to be 0.1 V. Or actually, it's better to keep it as 10 by 100 because the answers are in terms of fractions.
Sir, the volume decreases.
Oh, yes. So it's minus. Thank you. Volume decreases. Minus. Okay. Now that's it. You just have to find what is this X. I think because everything will cancel out. You can cancel the P's and you can cancel the V's. Because if you just take common out, that's what will be there. So I basically have 1 plus X by 100 is equal to if I just, it will be, oh, into is there. Okay, fine, we'll do it. Into 1 minus a 0.1, maybe 1 minus, okay, 1 minus, fine, let me keep it as 10 by 100 only. Okay, is equal to 1, right? Because this side is just 1, not 0. If you just put 0, that's it, right? Okay, right. So continuing, what you'll be getting is 100. This is 100 plus X into 1 minus 10 by 100 will become 9 by 100 is equal to 1, right? Actually, with this 100 into 100 will go there. So I basically have 1000 plus X is equal to 1000 divided by 9. And if X you want to find, it will be 100,000 by 9 minus 100. Correct? Am I doing something wrong? Because I don't think the answers will match. It might match. Okay, we'll check. So if that's the case, it will be
Sir, it's
9?
90 by 100.
90 by 100. Oh, okay. You're telling answer, final answer. Okay, okay, we'll check.
No,
Right.
sir.
Ah,
Just the 100 plus x on the right side, the first step.
here.
No, sir, on the top. 90
Oh,
by
here.
100.
It's 90. Oh, yes, absolutely. Correct. 90 by 100. Okay. So this is 90. Okay, fine. So I'll get 90 in the denominator, right? So now if I do that, it will be 90 into 1000. 9,000. Sorry, 90 into 100 will become 9,000 minus 1,000. Correct? So which will be, I mean, 2,000, right? Minus 1,000. Sorry. No, something I'm doing. Actually, that's why if you skip some steps, that's exactly what we have. Okay. 1,000 minus this into this. What? Oops, I missed a 0. 2 zeros. Okay, now it's fine. So this will be 9,000. So 10,000 minus 9,000 will be 1,000 divided by 90. Yeah, 100 by 9 is correct. That's the answer. That X percentage is 100 by 9 percentage. Okay, right? Now, I would have actually made this calculations very easy if I would have taken some numbers, in the sense that you would have just assumed that the initial volume was, initial pressure was 100 and the final pressure was 100. I mean, initial volume was also 100. So if it is X percentage, right, you would have had X plus, I mean, 100 plus X by 100, right, into 100 minus 10 by 100. So anyways, you'll almost end up with the same calculation. But anyways, you can just calculate X directly, and then you can do the reverse one. Find exactly the percentage. So that way also it will work. Okay. Anyways, right. So hope you understand. It's just simple mathematics what I did here, using P1 V1 equal to P2, and the percentages you have to add for pressure and subtract for volume. That's it. Right. Okay. Now 10th question, guys, quickly. Okay, I actually forgot to give you a formula. There is a formula directly for density using your ideal gas, right? That is equal to Pm by RT. But I don't think you have to use it here. Okay, fine, you can use it, right? So density is equal to Pm by RT. You can derive it if you want. It's pretty easy only, right? Okay, so density is equal to Pm. This M is molar mass of the gas. Okay, molar mass of the gas. If it's oxygen means 32. Okay, not the given mass. It's not going to depend on the given mass. It's going to depend on the molecular mass of the gas. Okay.
Sir, I'm getting the answer as 1.875.
1.875. Okay. Again, it's going to be pretty simple. Now you see in this particular case, molecular mass is going to be constant, R is a constant, and temperature you see initially 298 Kelvin, finally also 298 Kelvin. They're not changing the temperature, but they're changing only the pressure values. Correct, right? So I can write D1 by D2 is equal to P1 by P2. Is it not? Because you see density and pressure are directly related because all the other things are constants. That's it. You just have to use this. Maybe you might be getting 1.875. I'm not sure. Maybe I can check. Question number 10. Yeah, 1.875. That's it. Okay. So you can use this formula directly. D is equal to PM by RT. Right? Okay. I'll go to the next question. Okay, question number 8 and 9. Okay, first we go on to question number 8. So they're telling N2 gas under a given state 1 is to be changed to state 2. Right? Now they're asking, does N2 escape from 1 is? So you see there is the state 1 is 273 degrees Celsius, 3 atmospheric pressure, 1.65 liters. Right? Now it has gone to 0 degrees Celsius, 0.75 atm and 0.55 liters. Right? So you see everything is changing. T is changing, B is changing, T is changing, everything is changing. So obviously number of moles also has to change, right? So you just have to use ideal gas equation 2 times and just calculate how much percentage has gone out. That's it. Remember to use your temperature in Kelvin scale. If you don't do that, entire problem is wrong. Yes, any answers? Yeah, it's not a big deal. Maybe the calculation will be a little bit, but it's the problem is very easy. You just have to use ideal gas equation 2 times, right? So I know N. I basically know N, PV is equal to nRT. So I can write N.
Sir, I got the initial number of moles is 2 times the amount of moles that you get in the end.
Okay, so how much is the increase? How much percentage is the increase? You're getting twice. Initially, it was say 2. Now it is 1. So how much has gone up? 50%. Okay, but there are no options like 50%. Okay, we'll check.
I'll check.
Yeah. Cool. So PV is 3. Volume is 1.65, which is divided PV divided by RT. R is 0.08. Okay. Then temperature is 273. So 273 plus 273, that's the Kelvin, right? So 273, 473, 543, 546. Okay, 546, right? So this was whatever the initial number of moles. Now you can calculate N2 also, right? So that would be 0.75 into 0.55. Actually, it takes a bit of calculation, I understand. And we are not going to do the calculation, guys. I'm going to give you the answer directly. Okay, so 0.75 into 0.55 and 273. Right. Okay. Into again same 0.08. Okay, so you just have to calculate N1, N2. Now what you have to find out is the percentage escaped, and you can see how much has escaped is basically going to see, this is in terms of number of moles. First you have to convert this into the molecular, I mean the given masses. They have given it as N2. The molecular mass is 28, right? So basically it's going to be M, let's say 28 N1. That is what is one initial mass of the gas. Or actually, even if we do in terms of number of moles, it is not going to matter because they are eventually proportional. Okay, we don't have to worry about it, right? So
Sir, sorry, sir. I got it as N1 equal to 6 N2.
6 N2. So it is decreasing by 6 times. So that would be 1 by 6 is how much? 1 by 6 is 0.333. So it will be, oh, no. Wait, we'll do 1. Fine. Anyways, we'll just do it. So N2 minus N1. This is what is the left out thing. I want to take the percentage of this. So initially it was N1 into 100. This is what would have been the answer. Exact percentage you will get. Right. So you are telling that I'm getting N.
So the answer is 16.66.
Okay, understood. Yes. Okay. Fine. So now it's basically going to be 6 minus 1 is 5. Oh, wait. What am I doing? 6 and 2. Okay, fine. 6. This actually should be 6. Oh God, me and my studies. Never ending story. Okay, fine. So it's basically going to be 5 by 6 into 100. Yes, I think it'll be 16.6667%. Yes, that's the answer. Okay, fine. Now go to the ninth question. I hope everybody understood. It's pretty simple. I just used 2 times ideal gas equation and I calculate how much percentage has escaped. Right, you can do it in however way you want it to be, calculating the percentage. But this is pretty common. That is calculating N1 and N2, then do how much ever, however feasible you feel it to be. Okay, next question. 1 gram H2 and X grams of O2 exert a total pressure of 5 atm. Okay, at a given temperature, the partial pressure of O2 was 4 atm. So they're asking, what is the mass of O2 in the mixture? Okay, now tell me, should I use ideal gas equation here, or I should use something else here? There is one law which is going to help us. Not the laws which you studied in this chapter, but you used it eventually in your equilibrium chapter.
Dalton's law.
Yes, absolutely. You have to use Dalton's law of partial pressures. Okay, so pretty simple formulas. If you remember the formulas, okay, I'm not going to help you. I'll give you maybe 2 minutes to tell me the answer. Okay, any answers? Or at least the formula, if you remembered, right? So it's just PA is equal to P total into XA, right? So PB will be equal to P total into XP, and obviously total pressure will be equal to PA plus PB, or I can write P total is equal to P total into XA plus P total into XP. Obviously, this P total into XA into P total into XP is what is called as your partial pressures of A and B, PA and PB. Right? That's what you have to use it. But there are everything in terms of mass, so you have to know how to use mole fractions. Okay, so if I have to solve it, right, total pressure they have given is 5 atm, right? And in that they have given the total, this thing, what is that? What is PB? Okay, if I can write it as
the answer is 64 grams.
Okay, fine, we'll check. Right, fine. So if I do that, P total is again 5. Actually, it is gonna XA plus XP is equal to 1. Okay, this I can use. I can just use this one, first one. So I can write PA. They have given what is the mass of O2, sorry, pressure of O2, which is 4 atm. Okay, 4 atm is equal to total pressure is 5, right? And the mole fraction, right? They have given 1 gram of H2, right? So I just have to use the mole fraction of O2. So it is going to be number of moles of O2 divided by number of moles of O2 Number of moles of H2. Done. So this is going to be 5 into, I say they need the mass. So let me do it in terms of mass. So given mass of O2 divided by 32 divided by given mass of O2 divided by 32 plus it's going to be 1 by 2 number. Now given mass of H2 is 1, so this is going to be 0.5. Yeah, that's it. Okay, so you just have to do the LCM part and do everything, right? So I'll just actually give you the answer. This is question number 9. Yeah, 64 grams. Okay, so the answer, that is the mass of O2, is 64 grams. Okay, pretty easy, right? Okay, what is the next question? What is the time? Yeah, we can do a couple of questions. Actually, the questions here are not going to be useful. Let me give you a question. Take down the question, guys, or I'll just give you the summary of the questions. I have, say, 8 grams of O2 gas, right? I want to know what is the kinetic energy of this at 300 Kelvin. Okay, I have 8 grams of oxygen gas. Okay, and I'm asking you, what is the kinetic energy of this 8 grams of oxygen gas at 300 Kelvin? Okay, what is the formula which I have to use? What is the formula?
3 by
Sir,
2
if it's
RT
3 by 2
and
K.
Correct. So now the again the what is that, the chaos comes. Either it's going to be 3 by 2 KT, that is KBT, or is it going to be 3 by 2 RT? You tell me which can be used. What did I tell you? What is the difference? I know. Actually, I'll write the formula like this. KE will be 3 by 2 into N into KBT. And again, kinetic energy can also be equal to 3 by 2 into N into R into T. Okay, at least now can you tell me what is the difference? Yeah.
so here we can use the second formula now, sir, because we can find the number of moles easily.
Absolutely. That will be, it's not like we cannot use this, but it will be better to use this. Yes, correct. Right. So this N talks about number of molecules. I told you, if I don't include this N, capital N, this kinetic energy is for one molecule of the gas. Right. And if I don't include this N, that means it is for 1 mole of the gas. That's when I have to use R. Molecules, Kb, moles, R. Right. So yeah, as you said, I can easily convert directly mass into number of moles. But I can even convert mass to the number of particles. It's not a big deal. You can calculate the number of moles again, or I can say 32 grams of O2 will have 6.023 into 10 to the power 23 molecules of O2. So I can do that anyways, but this will be an easy formula to use. Ke is equal to 3 by 2 nRT. Right? You can calculate the number of moles. R value should be
8.314.
yes, right. We want all the kinetic energy in SI units. Okay. I mean, like SI units mean joules basically. I want in terms of joules, right? So obviously I'll go for 8.314. Yeah, that's it. Okay. So this is just a random problem I gave because no problem was good for this particular topic. Now we'll go for the next problem. Okay. Next question coming on your way. Okay, question number 12 and 13. So both you can see are previous year questions. One in 1996, another in 2000. So they're asking the ratio of root mean squared of speeds of H2 gas at 50 Kelvin and that of O2 gas at 800 Kelvin is what? So hope you remember the formulas. Root mean squared velocity or speed. What is the formula? RMS velocity or RMS speed.
Root 3 RT by M.
Yeah, right. Root of 3 RT by M. That's the formula for RMS velocity. So VRMS is root of
I'm getting the answer at once.
okay, we'll check. Right. So you can see 3 is constant, R is constant, only variables are temperature and molar mass. Right. So I can write V RMS of O2 divided by V RMS of H2. H2 is what is asked. Okay. Right. Will be equal to or okay, will be equal to root of so basically this 3 and R will get cancelled, only T and M will be remaining, right? So it is gonna be this entire, if I can make a bigger root, right? So can I say it's gonna be temperature of O2 into or divided by molecular mass of O2? Right, into right, into molecular mass of H2 divided by temperature of H2, right? Because they are division, right? So if it goes up, numerator becomes denominator, denominator becomes numerator, right? So you just have to substitute the values. So that would be temperature of O2 is what? 800 into divided by mass of O2. That is obviously I know molecular mass is 32 into 50 Kelvin. No, by 50 Kelvin. That was 2. Yeah. So if I just cancel, this would be how many times? 1 time, 16 times. Am I right? Yeah, 16 times. So this 2 times, yes. Root of 1, this whole thing root. Answer is 1. The ratio is 1. Correct. Okay. Next question. 13th question. Just so you can understand, if you just know the formulas in this chapter, you can score whatever the marks the questions are gonna come. Right.
So I got the
Actually,
answer as option C.
that is for 13th question. Is it 13th question you're telling?
Yes.
Okay, fine.
Yes.
Yeah. So I think it's going to be same formula, root of 3 RT by M, right? So the RMS velocity of hydrogen gas is root 7 times the RMS velocity of nitrogen gas at say at same temperature, right? That's what they mean. So what? Oh, no. Right? RMS velocity of hydrogen gas is root 7 times the RMS velocity of nitrogen gas. If T is the temperature of the gases, whatever, the hydrogen gases and the nitrogen gas, then what is lesser, what is higher? That's what they're asking. Right? Okay, so again, you just have to use the formula. Same thing, same formula I can use, this same formula. Right, whatever you have used here, but instead of O2, I have to use N2. And you just have to see what you're getting for the temperature. I don't think it will be root 7 times because maybe I think the answer should be for C. The answer should be C. Okay, we'll check. So yeah, like what is the higher RMS velocity of hydrogen gas to the RMS velocity? So okay, velocity of H2 is root 7, right? Okay, which is equal to, or I can just cancel the roots. Okay, that will be better for me. Okay, fine. So that would be temperature of H2 divided by temperature of N2 into molecular mass of N2, which will be 28, divided by molecular mass of H2, which is this thing. What is that? 2, right? So this and this will go how many times? 14 times. Right? So it should be basically TH2 divided by Tn2 basically is going to be 7 by 14. 7 by 14 is going to be 1 by 2. Right? So what do you mean by this? That means temperature of H2 should be, or temperature of N2 is twice the temperature of H2. So obviously temperature of H2 should be greater. Am I not correct? So this I can write it as T of H2 should, or 2 into T of H2 is temperature of N2. Yeah, so obviously temperature of N2 should be greater. So answer C is correct. Yes. Okay, what is the time? Fine, guys. I think we just have to do some 2-3 more problems and then we'll wind up. So tell me which chapter you want to start. You want to start with atomic structure or you want to go back to organic? Next class. What do you want? Or anything is fine.
Sir, atomic structure.
Okay, fine. So we'll go for atomic structure. Fine. Okay. Thank you, guys. We'll meet again. Okay.
Thank you, sir.
Yeah.
Thank you.
Thank you, sir.
Yeah. Thank you.